History time. In the 17th century, a guy named Isaac Newton asserted that he was him by releasing a way of describing motion using forces. 100 years later, Joseph Louis Lagrange said, "Nah, chief, let me cook," and found another way to describe motion using the principle of least action. Hamilton did some stuff too, but you get the point. Anyways, later on, two men named Gibbs and Appell independently discovered what we conveniently call the Gibbs-Appell equations of motion, which turned out to be super useful for complicated systems such as nonholonomic systems, where Newton's formulation is too simple and Lagrangian's has really hard math. We can start defining the Gibbs-Appell equations of motion by relating the Cartesian coordinates to the generalized coordinates of the system in a system of n particles. We can easily write the formula for a small change in r in terms of the generalized coordinates. We take the second time derivatives of each side of the partial derivative. To avoid confusion, let's say that the generalized acceleration q double dot is alpha. To solve for the work done over a small displacement, we can say that it's the sum of generalized forces times the small change in generalized coordinates. This can equivalently be done in Cartesian coordinates. F equals ma, so we make that substitution. And let's also substitute the small Cartesian displacement with the above expression. We can manipulate the sums, and we now have an expression for the generalized force. Next, let's define S to be half the sum of masses times the squares of Cartesian accelerations. We take the derivative with respect to alpha of both sides, and we're left with the same expression as we had for generalized force. So we can say that the partial derivative of S with respect to alpha is equal to the generalized force. This is Appell's equation of motion and was discovered in 1899. Much more recently, though, there was a modification that was proposed. First, let's talk about pseudo-velocities. We define a component of the pseudo-velocities to be a linear form of generalized velocities. Those coefficients are functions of the generalized coordinates. One place where you encounter pseudo-velocities is when you project angular velocity in Eulerian angles, for example. We can also write each component of the generalized velocities as a linear form of the pseudo-velocities. The A's and B's can be thought of as matrices that are related by these sums, where the right side is a Kronecker delta. Well, what about pseudo-coordinates? While pseudo-velocities aren't always integrable, we can define the differential of a pseudo-coordinate as a linear combination of generalized coordinates. The time derivative of a pseudo-coordinate corresponds to a pseudo-velocity. We can use the coefficients of the linear forms to relate the partial derivative of any function with respect to a pseudo-coordinate to its partial derivative with respect to generalized coordinates. This can be used to prove that the partial of a Cartesian velocity with respect to pseudo-velocity is equal to the partial of Cartesian position with respect to pseudo-position. We can also rewrite generalized forces as pseudo-forces. It follows from the previous relations that the partial derivative of S that we defined earlier with respect to pseudo-acceleration equals pseudo-force. Now let's introduce a new quantity r, which is the sum of products of Cartesian forces and accelerations for all the particles in the system. It happens to be that the partial derivative of this with respect to pseudo-acceleration is also equal to the pseudo-force. Let's define the Gibbs function to be the difference between S and R. It follows that if you take the partial derivative of g with respect to pseudo-acceleration, you just get 0. This is the Gibbs-Appell equations of motion as reformulated by Edward Desloge in the late 80s. As an example, let's think of a simple pendulum. We can describe its position in terms of the angle phi it makes with the vertical. Let's convert that to Cartesian coordinates. Now, let's take the time derivatives to get velocity. And acceleration in Cartesian coordinates. Plug it into the expression for the Gibbs function, and remember that force is just mg. Notice I chose our pseudo-coordinate to be phi, so the derivative of the Gibbs function with respect to the second time derivative of phi is 0. So let's differentiate both sides of our expression for the Gibbs function with respect to pseudo-acceleration. When you simplify that, it's just the same equations that you would get from the Lagrangian formulation, or any other for that matter. In a future video, we'll cover nonholonomic systems, specifically a rolling penny, and determining its stability. Thanks for watching, and I'll see you next time.